We all know the elementary school story. An apple falls from a tree, hits Isaac Newton on the head, and he defines gravity. But if you rely on that simple, intuitive narrative for the BPSC exam, you will likely struggle with the physics section. Gravity is one of the 4 fundamental forces of nature. It dictates the structure of the universe and holds the planets in their orbits. Yet, surprisingly, it is the weakest force of the 4. It takes the entire mass of the Earth just to pull a single apple to the dirt. BPSC examiners know exactly how human intuition works. They rely on a specific set of physics myths, a mental trap board, to generate multiple-choice questions designed to exploit common misconceptions. Success in this section requires looking past what feels right and identifying the specific mechanics the physical laws actually dictate. Let's start with trap number 1. The assumption that a capital G and a lowercase g represent the exact same concept in mechanics. This graphic displays Newton's universal law of gravitation. Capital G is the universal gravitational constant. Measured by Henry Cavendish using a torsion balance, it's a scalar constant. Its exact value is an absolute rule, remaining the same regardless of medium, temperature, or altitude. Compare that to the right side of this matrix. Lowercase g represents acceleration due to gravity. It's a vector quantity that changes based on location. Crucially, as highlighted at the bottom, g does not depend on the falling body's mass. Whether you drop a feather or a solid iron anvil in a vacuum, the Earth accelerates them both at the exact same rate. Mixing these 2 variables leads to incorrect calculations. Capital G represents a universal baseline, while lowercase g is a localized environmental effect. That local effect brings us to trap number 2, the assumption that little g is exactly 9.8 meters per second squared everywhere on Earth. Earth is not a perfect sphere. It bulges outward at the equator. Because the polar radius is smaller, standing at the north or south pole places you physically closer to Earth's center of mass, maximizing gravity. Moving to the equator, we introduce the centrifugal effect. As the Earth spins, it creates an outward centrifugal force that counters gravity. This reduction means the effective value of little g reaches its minimum at the equator. If you dig beneath the crust, gravity decreases linearly. If you calculate g at the exact center of the Earth, the surrounding mass pulls equally in all directions, making the net acceleration exactly 0. Because little g fluctuates based on altitude, depth, planetary shape, and spin, your weight, the gravitational force acting on you, changes based on location. But your mass, the actual quantity of matter inside you, remains absolutely constant. That distinction clarifies trap number 3, a frequent BPSC trick question. The myth that astronauts float because they've moved beyond the reach of Earth's gravity. Look at these astronauts in training. Gravity is fully present. In orbit, Earth's gravity provides the centripetal force keeping a spacecraft circling the planet. They float because both the astronaut and the vehicle are in a continuous state of free fall toward Earth. The sensation of weight comes from apparent weight, or normal reaction, the physical floor pushing back up against your feet. When the floor falls away at the exact same rate you do, that normal reaction drops to 0. This diagram illustrates Kepler's second law, the law of areas. Notice the callout on the right. A satellite's orbital speed is not constant. Conserving angular momentum, planets move faster when their elliptical orbit brings them closer to their host body. Weightlessness in orbit is an illusion of relative motion, not an absence of gravitational force. 2 satellite facts are frequently tested. Geostationary satellites must revolve in the equatorial plane, from west to east, matching Earth's rotation. Conversely, polar satellites are primarily utilized for remote sensing. This trapboard summarizes the final numeric myths. Look at the green note. Escape velocity from Earth is 11.2 kilometers per second and doesn't depend on projectile mass. Next, the blue note. Orbital velocity decreases as the orbit's radius increases. Make sure to screenshot this board for your revision. Separating universal constants like big G from environmental variables like little g allows you to identify the specific logic gaps examiners rely on.